Today, we're learning about periodic trends. Okay? We've already established that the periodic table is organized so that atoms with similar properties are in the same column, and we learned how they're organized by period based on their electron configuration. Today, we're going to see how that electron configuration causes their properties to exhibit patterns on the periodic table. Okay? And those patterns that we're going to look at, that you should be able to tell me what it is and what the pattern on the periodic table looks like by the end of class, is for atomic radii, ionization energy, electron affinity, and electronegativity. We're going to talk a little bit about ionic radii as well, so the radii of ions, and that's connected to atomic radii and its pattern on the periodic table. Okay? And then we're also going to be able to explain why those patterns don't always hold exactly the same for the D block elements. Okay? All right, let's just jump into it then, shall we? So, the arrangement of electrons around the nucleus, aka electron configuration, that's what we call that, has an effect on the properties of elements. So, many properties exhibit what we call periodic trends, or patterns on the periodic table. We're going to look at several today. The first of those is going to be atomic radius. Atomic radius is the distance between the center point of a nucleus and the outer edge of its outermost orbital. But if you remember, orbitals are areas of probability, so their edges are kind of fuzzy, and finding the edge to measure would be a real challenge. So instead of trying to measure the edge of a fuzzy cloud of probability where an electron may or may not be, we measure atomic radius by finding two identical atoms that are bonded together and measuring the distances between their nucleus and dividing it in half. And that will give you your radius of your atom, but it's just a much more reliable way to measure it. In general, atomic radius is going to decrease across the period. So that means the radius is going to get smaller as we go from left to right across the periodic table in the same row. This is because even though we're adding electrons to it, and so your brain would be like, well, if we're adding electrons, shouldn't the radius get bigger? Well, we're adding them to the same energy level. And if you remember, the energy level tells you how far away from the nucleus you are. So long as we're adding them to the same energy level, that shouldn't increase the radius. And we're also adding protons to the nucleus, right? Helium has more protons in its nucleus than hydrogen. More protons means a stronger positive charge, and a stronger positive charge means a tighter grip on those electrons. So they're getting pulled in more towards the center. So as your nuclear charge increases, your radius is going to go down. However, the force from the nucleus is offset by electron repulsion. So there's only so close you can pull two electrons. Because remember, like charges repel each other. So if I'm trying to shove two electrons into a teeny tiny spot together, they're not going to want to go there, right? So the closer you pull them in, the more they fight each other. So what that means is that while the radius does still get smaller as we go across, it gets smaller by less and less every time. So I want to point out to you a picture in your book, and it's okay if you don't have your book just the second, okay? But on page 149 in your book, there's a table that has the chart on it that has the visual representation of atomic radii, okay? And it has both a numerical value, so like a measurement of their radii, and then also, like we had on the pictures that we used for the Mendeleev lab, an actual visual representation of relative sizes of the elements. So, the difference between lithium and beryllium, between their atomic radius, is lithium has a radius of 152, and beryllium has a radius of 112. So notice how much of a difference there is how much smaller the radius is, okay? When we get all the way over to fluorine and neon, fluorine's atomic radius is 72, neon's is 71. So it still got smaller, right? But just not by as much. That's what this last point is about. It's saying after they get so small, it can't get much smaller because those electrons start to repel each other. So it's going to get smaller as we go across the periodic table, but by less and less each time.
So then what about...
So you'll notice how this says in general. And you're going to see and hear me say the words in general a lot, because while there are general trends, there are exceptions to those trends. And usually I will talk to you roughly about a difference in trend. Okay? The trend down the group is that you should see atomic radius increase as we go down the group. Okay? Now you may be saying to me, Mrs. Von Lau, I thought you said that as nuclear charge increases, that the radius should get smaller. And while that is accurate, that only works when we're only adding electrons to the same energy level. As soon as we are increasing energy levels, we're moving electrons further from the nucleus, and as a result, we're going to have a larger radius. So even though we increase nuclear charge as we go down, we're also adding electrons to more energy levels as we go down. And so they're getting farther and farther from the nucleus, and as a result, the nucleus is going to get larger. There are sometimes exceptions to this. For example, if you look at gallium, you'll see that gallium is significantly smaller than aluminum, despite being below it in its group. And the reason for this is because of the D block elements. So if you look at aluminum, right, the difference between magnesium and aluminum is just one proton. But because between calcium and gallium, there's actually an 11 proton difference because these D block elements are here, that means gallium has a significantly stronger nuclear charge than aluminum does, right? Which is the reason why it has such a small radius compared to aluminum, even though it has electrons in a higher energy level. There's just so many more protons involved that they overpower that. So we see a little exception there. All right. Let's talk about ions. When you add or remove electrons from an atom, you're going to get what's called an ion. An ion can either be a singular atom or it can be a group of atoms bonded together, but in order to be an ion, it has to have a positive or negative charge on it. There are two types of ions. If it's a positively charged ion, we call it a cation. And if it's a negatively charged ion, we call it an anion. Any process that's going to result in an ion being formed is called ionization. And that's important because we're about to talk about ionization energy. So our next trend that we're going to talk about is ionization energy. This is specifically the energy required to remove an electron from a neutral atom of an element. So if we're removing an electron, we're taking away a negative charge, so our ion will be positively charged. So the ions we're talking about right now are cations, positive ions. All atoms require energy if you are going to remove an electron from them. You got to have energy to do that. However, how much energy you need is different depending on the atom, and there are trends that appear on the periodic table. Okay. In general, ionization energy should increase across the period. So from left to right across the periodic table, you should see that ionization energy go up, meaning that it becomes more difficult to remove an electron from that atom. This is due, once again, to increasing nuclear charge. So for the same reason that the atomic radius shrinks because those electrons are being held more tightly, it's also more difficult to remove an electron, so ionization energy goes up. So they're opposites of each other, but for the same reason. Okay. And it's going to decrease as you go down the group. Okay? Again, the electrons are farther away from the nucleus, they are held less tightly, and as you add energy levels, there are more and more electrons between the nucleus and those outer electrons, which means they're shielded from that positive nuclear charge and held less tightly. Okay? So both their distance from the nucleus and how many electrons are between them in the nucleus cause those outer electrons to be held less tightly. So as you go down the group and those energy levels increase, you see ionization energies go down because it's easier to remove those electrons. And so remember, ionization energy is a measure of how difficult it is to remove that electron. How much energy do I have to put in? And just because of their placement on the periodic table, ionization energy is higher for nonmetals than it is for metals. Metals are much more willing to give up one of their electrons, so they have lower ionization energies than nonmetals do. It is possible to remove an additional electron from an already positive ion. So if you have an atom and you remove an electron from it, it becomes a positive ion. It's possible to go back in and double dip and take another electron from them. Okay? These would be called second and third ionization energies. So the ionization energy that is shown on that chart in your book is for the first electron. Then if you want second and third ones, those have different ionization energies, and they're always going to be bigger because removing a second or third electron is more difficult. Okay? The atom is already positive, more positive, so it's holding on even harder than it was before. So, going to be more difficult to remove that. In addition to that, if your second or third ionization energy requires you to remove an electron that's not in the outer shell, you have to dip into those core electrons, it will be even more difficult. So, for example, if you were trying to get at calcium, okay, it's got two outer shell electrons, right? So if you remove both of those and then you try to go back for a third and you have to go to that inner shell instead of the outer shell because you took all of those, it's going to be much more difficult. Require more energy even, okay, because they're closer to the nucleus, they're being held tighter. It just becomes more and more difficult the more you want to take, okay?
I think of that as like there's...
All right. Electron affinity. This is the other side of the spectrum. This is the energy change that occurs when an electron is acquired by a neutral atom. So when an electron is added, this is the formation of an anion. Okay? Notice that I said energy change. Okay? For ionization energy, it's always an energy requirement. It always requires energy to remove an electron. The same is not true for electron affinity. Sometimes it requires energy and sometimes it doesn't. Okay? For some atoms, they want another electron. So adding an electron to them is very easy. And in fact, it's so easy that sometimes you get energy back instead of putting energy in. So instead of requiring energy, energy is released. These electron affinities are represented by negative numbers. Because if we're measuring how much energy it takes to give them an electron and they give you energy back, that's a negative energy requirement for you. For some atoms, adding an electron is very difficult and they do not want one. And therefore, you have to give them energy in order for them to take one. These electron affinities would be positive numbers if we could measure them. But measuring them is very difficult because the atoms you create are extraordinarily unstable because they don't want that electron. So as soon as you stop putting energy in, they let right go of it and they just lose it spontaneously because they don't want it. So it becomes very difficult to measure how much energy you're putting in because of how unstable they are. And as a result, if they would have a positive electron affinity on the chart in your book and in data tables, their electron affinity is represented as the number 0. And we just simply know that they don't want that electron. The larger the negative number, the easier it is, the more they want to gain an electron. The smaller the negative number, the less they want to gain it. And if it's 0, then they just straight up don't want that electron, and you will have a very hard time giving it to them. In general, the trends for electron affinity are that it becomes more negative as you move across each period in the P block over here. Okay, so you're going to see it become more negative over here. And it's going to become less negative as you go down a group. So remember, more negative means it's easier to add an electron. Less negative means it's more difficult to add an electron. As you go down the group, you'll notice on the chart that this is less regular than going across a period. And that's because there are two competing factors at play here. So the things that affect electron affinity are that as your nuclear charge increases, your electron affinity should also increase. So it should be easier to add an electron. As your atomic radius increases, your electron affinity should decrease, so it should be more difficult to add an electron. The result is that usually size wins out, so that's why usually as you go down a group, you'll see that electron affinity become less negative. But when you get into the transition metals in the middle block there, their sizes are usually pretty similar. Their sizes don't change that much. And as a result, you will sometimes see that trend that it just doesn't hold up in the transition metals. It's possible to add an electron to an already negative ion, so to give it a second electron. But just like with positive ions getting an extra electron removed, it's more difficult the more of them you try to add. So just like when we tried to remove additional electrons and it got more and more difficult, adding additional electrons gets more and more difficult. All right, when atoms become ions, their radii are going to change. Okay, so if you lose or gain electrons, obviously that's going to affect your atomic radius because those electrons are involved in that process. Positive ions, these are formed by metals usually. They're the ones who usually tend to form cations, and your cationic radii are going to decrease across the period. So just like with atoms, they're going to decrease as you go across the period. The electron cloud is shrinking because of increased nuclear charge. And negative ions, these are formed by atoms that start roughly in group 15, and they form those anions. And anionic radii also decreases as you grow across the P block for the same reason that increased nuclear charge is going to cause them to shrink. And as we go down the group, both cations and anions tend to increase their radii. Electrons are still being added to those new energy levels, so just like with atomic radii, ionic radii are going to increase down that group. So, in general, what you should note from this is that the trends for atomic radii and ionic radii are very similar. You may start with a different radii simply because you are an ion, but the trends still hold true for them. They are not exempt from the forces of the nucleus or the electron cloud. Chemical compounds form because electrons are either lost, gained, or shared between atoms. Okay. The electrons that interact in this way are going to be the ones that are in those highest outer energy levels. Okay. We call these valence electrons. So you may have heard me use this term before because I'm very used to using it, and sometimes I forget that you don't know it yet, but now you will. Valence electrons are the electrons that are available to be lost, gained, or shared in the formation of chemical compounds. So when I say valence electrons, I'm talking about the electrons in the outermost energy level, the ones that would be able to participate in bonding. For many main group elements, the outermost S and P sublevels are the valence electrons. Okay. Sometimes both S and P electrons are involved, and sometimes it's just those electrons that are in the p orbitals. Electronegativity is a measure of the ability of an atom in a chemical compound to attract electrons from another atom in the same compound. Okay, so those valence electrons, the ones that are involved in the bonding, are around the molecule, the new compound that's been made, but they're not evenly shared. So, for example, in a water molecule, we have two hydrogens and an oxygen, right? The hydrogens each provide an electron to be shared with oxygen, but those electrons spend more time around the oxygen than they do around the hydrogens, because oxygen is more electronegative than hydrogen. Okay, so electronegativity is just measuring how much pull do they have on those shared electrons. Fluorine, the halogen, is the most electronegative atom on the periodic table, and they arbitrarily decided to give it a value of 4 for its electronegativity. And then they calculated all the other values of electronegativity in relation to the value they gave to fluorine. So essentially, we're just comparing how electronegative they are with how electronegative fluorine is. In general, the trends for electronegativity are that it increases across periods, so from left to right. There are, of course, exceptions to this, but in general, it increases left to right. And it decreases or sometimes remains the same as you go down a group. Some noble gases never form compounds, and so it's impossible to assign them an electronegativity, because how can we assign them a value of how much they pull on shared electrons if they never share electrons? It's not possible, right? So instead, we have to give them a value of 0. So you'll see, or not of 0, but you'll see on the table that they have just like a dash under their name that's just saying we don't have a value for them, they don't form compounds. In general, D-block metals are very similar to each other in their properties. Okay. This is because they have between 1 and 2 electrons in their s orbital, and then somewhere between 1 and 10 electrons in their d orbital. And as a result, both d and s orbitals are available to interact. And the fact that those d electrons are also able to interact causes some interesting characteristic properties for elements of the D block. And it causes some changes in the way that their trends happen. So we're going to talk about those trends specifically for the D block. Okay? Trend number 1, the atomic radii still decreases, but it decreases much less than it does for main group atoms. Okay? This is because those electrons that are getting added to that inner orbital are shielding those outer electrons from the nucleus. So we are adding more into that inner level and causing more shielding happening, And so they're going to decrease still because the nucleus is still getting stronger, but not by as much. You'll notice halfway through the D block that the radii reach their lowest point, and then they actually begin to increase again as you exit the D block. And this is because as you add more and more electrons to that D orbital, those electrons start to repel each other and cause that electron cloud to increase in size, so the radii grows slightly. So instead of just like the rest of the atoms on the periodic table, instead of just getting smaller as you go left to right, it gets smaller to a point and then actually slightly increases again. The ionization energy for D block elements usually increases down the group because those outer electrons that are available for ionization are shielded from the nucleus by d orbital electrons. So it's easier to take those outer electrons because there's all of those d orbitals electrons in there shielding them from the nucleus. And while the radii for cations and anions follows the expected patterns from the table, it's important to note that D block elements are known for forming +1 cations, +2, and even sometimes +3, meaning that it's possible to remove sometimes up to 3 electrons from them. Okay? They're willing to give those up. And all D block elements have electronegativities that are ranging between 1.1 and 2.5, which follows the general trend of having electronegativity increase as the radius gets smaller.